Hello everyone, and welcome to this video poster session for Team 25 for the EPFL rocket team here in Lausanne, Switzerland. This year at the SA Cup, we're competing in the 10,000-foot SRAD-built hybrid rocket engine category. Our project this year is an iteration of last year's project, with the ambitions to make it lighter, faster, and overall better integrated, even though we are during a pandemic year. Our rocket this year and our project this year is called Belle Nuit 2.
Subsystem. Here we'll stay on the ground. This is our ground station, a fully portable mission control center that communicates with the flight avionics, the engine, as well as our GSE and the launch rail. In the current configuration, it can communicate with devices up to 10 kilometers away and has a full launch day battery life. The ground station also has its own secure launch control system, which features the necessary big red launch button as well as a fully SRAD interface developed by the team. We also have our own GSE for our engine, which has a plumbing system as well as some electronics to control actuators and give sensor data back to the ground station. Our GSE also features a fully SRAD visual link system. This makes sure that we have a direct visual link with the launch rail at all times during operations for minimal latency. This year we have also made our very own launch rail, which was designed, manufactured and assembled entirely by the team from scratch. Even offers full tilt and azimuth control during operations. And finally, our fully SRAD disconnection system, which manages the disconnection of our oxidizer filling hose quite gracefully. To test all this, many tests were done, including this range test to verify that our antennas were functional and that they met the requirements that were imposed. Ground segment is go for launch. Over.
The first year was mainly to read and understand the literature about rocket engines, and we also have initial dimensioning of the rocket motor. Then in the second year we did all the manufacturing of the hybrid motor and the testing. For the early design of the tank, we decided to have two versions, one with the caps screwed on the main cylinder and the second one with the caps welded, and then heat treatment to... non, je ne vais pas aller trop dans les détails. The early design of the tank included two versions in order to secure and decrease the risk of malfunctions. 5, 4, 3, 2, 1, ignition.
Avionics is the brain of the rocket. It is responsible for flight control and the communication with the ground station. All this is done thanks to this module, which was completely designed and assembled at EPFL. It is made of several boards called host boards. Each board can interface a slave peripheral, which is responsible for data acquisition and the radio communication, and so on. The host boards are interconnected with the CAN bus. This link extends to the propulsion subsystem. This year, we have improved our radio communication system. Tests have shown that we are able to communicate up to 5 kilometers without any problems. This pink buckle is attached to the recovery subsystem and allow us to recuperate the bottom half of the rocket.
The recovery module hosts all the recovery's electronics. All the components fit on a custom designed and 3D printed module. It is then glued on a 10 mm thick aluminum plate, which is screwed inside a custom coupler. All the parachutes, the necessary shock cord, and the module are hosted inside a carbon tube, at the end of which is the first event mechanism. The second event mechanism consists of 2 servo motors, a rigid joint, and a 3-ring mechanism. This mechanism is usually used to release emergency parachutes during skydiving. We adapted it to our needs. It is a great solution because all the forces do not act directly on the rigid joint, and it is easy to release the mechanism. To control all the events, we have 2 avionic cards, the Altimax, which is a certified one, and Cretec, which is students made. It's easy to program, and it allows us to do a lot of testing and to have our own algorithm. We had the opportunity to test our recovery system during drop tests, one from a cable car in Crans-Montana and one from a helicopter above Science Airport. The drop tests are great because they allow us to validate and certify our mechanisms. As the recovery subsystem, we work closely with the structure subsystem. It is important because the first event separation mechanism separates the
structure
rocket into 2
subsystem
parts.
is composed of many different modules which each hold a different subsystem to allow for easier integration. These are held together by couplers. The couplers are based on the Marmon principle and allow for us to mount and dismount the different parts of the rocket individually before assembling the whole thing. These are bonded to the composite tubes, either made from carbon reinforced polymer for the main parts and some flax fiber parts for the ones that need radial transparency. In the middle of the rocket, one of the normal couplers is coupled to the separation mechanism, which is one of the highlights of our design this year, as it is the first time that we're implementing this concept. The separation mechanism is made from the same principle of the Marmon clamp principle as the couplers. However, it has a wider angle in order to ensure the separation. There are 4 screws to give an initial preload for the separation when it separates, and it is held together with a tensioning screw on one side and a dynamo wire, which will burn thanks to current passing through a nichrome wire when the separation must occur. The only part of the rocket which is not made out of composite is the tank. The structural tank is made in 3 parts with the 2 caps welded and then annealed onto the middle tube and then machined to ensure that it's precisely perpendicular to not have a banana rocket.
ERT's 2021 payload project started 1.5 years ago. The first 6 months, a team of students from the EPFL physics department laid the theoretical framework of this year's experiment, an energy harvester. Looking for exotic ways to harvest energy from the rocket's flight and turning it into electricity, the team experimented with multiple designs. The final system consists of 2 mechanical energy harvesters who have to convert the rocket's vibration into electricity. One is a compliant mechanism which houses piezo element between anvils and uses a mass to harvest vibration on the XY plane, and the other is a linear induction system which is used in a control experiment. The compliant piezo harvester has been built in nylon using SLS 3D printing techniques, resulting in a robust part that weighs only 36 grams and can withstand many thousands of flexure cycles without breaking from fatigue. The whole experiment is monitored by our brand new Avionics. It consists of a layer of battery boards and a main computation board which houses multiple sensors, a microcomputer and a radio antenna unit. It is fully modular and can adapt to all the mission requirements of the future payload team. We are proud to show you the results of months of research and design poured into this new payload and cannot wait to share more about it with you.
The simulation subsystem is in charge of predicting the flight of the rocket using computational tools. So in general, we use rigid body simulators like OpenRocket, but we also developed our own simulator because we wanted to have like more flexibility in implementing new features, but also modifying the theoretical models inside the simulator. We also use computational fluid dynamics to characterize some aerostructure components like the air brakes, or to investigate how some flight parameters can have an impact on the rocket performance. To check the physical accuracy of those simulations, it is usually necessary to validate them against experimental results, and this is precisely what we did with Bella Louis 2 recently. So we ran a wind tunnel test at Sober, which is a local Formula One team, to gather some data on the real aerodynamic performance of the launch vehicle, so that we can then compare those results to the ones that we got from the simulations, and therefore fine-tune the simulations based on those results. Thanks to those simulations, it is possible to draft a precise ConOps, which is going to be presented now.
Okay, so for the concept of operation of the Bella Louis 2 rocket, we have three phases. The preparation of the rocket and the systems, the ascent and the descent. Starting off with the preparation, we have module integration, launch checks, launch pad setup, arming and tank filling. Depending on the conditions of the environment around the rocket, this can take up to 30 minutes. We can then prepare the ascent phase, where we disconnect the filling hose, we fire the motor, take off. Depending on the configuration, we would have thrust control or not, and then motor burnout. Then we continue the ascent with a ballistic flight of approximately 16 to 18 seconds. We have apogee, where everything went well, and we can go on to the final phase of descent. This is the recovery phase, where we have the primary recovery with a drogue, allowing for a fast descent of 90 seconds at 25 meters per second, and then secondary recovery with the main parachute with a slow descent at 5 meters per second. Once we reach the ground, we have touchdown, and we can start the ground recovery and disassembly of the ground segment. Once we have everything packed up, we can inspect and disassemble the rocket and the systems, and we are done.
A rocket is an incredibly complicated system. There's basically 1,000 ways that a flight could go wrong, and really only one way that it could go right. And it's our job as system engineers to make sure that that one chance does happen. From the very beginning of the project, we're the ones responsible for making sure that all the risks are mitigated and are as low as possible, that all the requirements are fulfilled, and just in general, the overall tracking of the design, of the structure, and of how we manage the project is done by us. So, in order to do this, the entire system engineering team here at the EPFL rocket team had to be incredibly coherent in our thought process and how we organized ourselves, because dealing with the global pandemic was very difficult. Communicating information and making sure that all the different subsystems, team leaders, team members worked well together and were integrated properly to come to and create the rocket that we really wanted and deserved was definitely a challenge for us, as I'm sure it was for every single other team. In order to do this, just like other years, but perhaps a bit more difficultly this year because everything was done online, we organized our design reviews, both preliminary and critical, early on in the design phases of our rocket, trying to, again, assess for the best possible outcome and solutions for the problems that we were facing that would fulfill the requirements and have low risk. Leading a team throughout such a complex system during a pandemic is very challenging, and it was our job to make sure that everyone had the necessary information and could communicate well with one another throughout the year. Obviously, this was more difficult because everything was done online, but we tried to deal with it with the best of our ability, and we hope that the final result that we have is up to the challenge and will meet the goals that we have set ourselves. Again, from the EPFL rocket team, we'd like to thank you for your attention and for listening to us during these last 15 minutes. Coming up, we'll be opening things up to questions to hope and continue the conversation with you, and so that we can help you learn more about our project and that we can share more of the passion we have for rocketry.